Welcome to the tutorial. My name's Evan Remington. I'm a postdoc in the Jazzieri lab. I don't have any particular association with OpenMind. I just happen to be somebody who volunteered to give this talk last year. And so this year I'm going to give sort of a condensed version of it. It's pretty basic, so if you've been using OpenMind for a while, you probably won't get much out of the first part that I'm going to give right now, but hopefully this will be useful to beginners through somebody who knows how to use the cluster but may not know all the best practices and all the details. So the objectives are to learn the basics of how to use OpenMind, to learn about what Slurm is, how it works a little bit, see some example workflows, learn how to use the cluster effectively, both for yourself and so that the resources are used efficiently for everybody. And then more generally, some strategies for using remote computing resources, which I think is what Satra is going to be focusing on for his part of the discussion. So along the way, we're going to learn how to use the terminal. If you don't know how to do that, going to get a short introduction to a shell script and learn some of the basics of Linux operating systems. So what is OpenMind? OpenMind is a group of computers which are all networked together. These computers are called the nodes, and they're accessible through a single portal called OpenMind. Well, this is old. It's OpenMind 7 now. Are we going to change that back to just OpenMind, or is it always going to be 7?
When we want to throw people.
In this array, okay, good. So this enables users to connect to this system and run computing tasks in a high throughput fashion. There's different types of nodes with different resources. I think right now there are about 50 some odd nodes with about 20 cores each, about 256 gigs of RAM, and some of them have GPUs. There is a lot of dedicated disk space on OpenMind. There's two kinds of disk space. There's your home directory, which you use to house code and things like that. And then there's the ohm partition, which is a high-speed special file system to work with all these nodes. Each group gets 10 terabytes of space allocated on this partition. And you can get more, but I think it's sort of limited in whether you can get more on that special partition. There's a fiber link to MIT for fast communication. There are some possibilities for expansion, but I think those are subject to space constraints. And there is a yearly fee of $2,500 per lab or group. But I think there is a short trial period that you can try if your lab hasn't already done that. So the architecture, there's a login node. So when you log in, you're going to be logging into openmind7.mit.edu. You can use this for your interactive terminal use and code development. And then there's the compute nodes, which run batch jobs or interactive jobs for both single and multiprocessor tasks. They have URLs like node 001, 2, 3. But typically, you won't be connecting directly to these nodes. You're going to be interfacing only through the login node. To get an account, you go to GitHub. I can add the. I don't know if the document I sent out has the GitHub page for OpenMind, but there's a GitHub page for OpenMind. Mainly, it's used for submitting issues. Like if something's not working, or you don't know how to do something, or you just have a question, you can submit an issue to this GitHub repository. It's not really a repository. So you just submit an issue that is formatted exactly like this. You have to be either on a trial run or be paying the yearly fee at this point. And as part of getting this account, you'll be subscribed to the OpenMind announcement list. So how does OpenMind work? typically, when you use a computer, if you're using the terminal, you type in a command, and the command runs. Here, there's sort of an added layer on top of that. You submit your commands to an application called Slurm, which is an acronym for a simple Linux utility for resource management. It's an open source workload manager for Linux clusters. It's very popular. It's used on a lot of the world's largest and most powerful computing clusters. What it does is it allocates access to resources. And resources are things like cores and memory or GPUs. And it provides a framework for starting, executing, monitoring, collecting output on these nodes. And it arbitrates the contention for resources by managing a queue of jobs. So let's say 100 people want to submit 1,000 jobs each. The cluster's not going to be able to run all these jobs right away. So these jobs go into a queue. And when Slurm decides that job 90 it's its turn to run, then it runs it. What do you need to connect to OpenMind? So this is about the point where I suggest that for those of you who can follow along on your laptops, you'll need a terminal emulator. I suspect most people here are using Macs. There's an application called Terminal that you're going to be working in. And there's other things you can use as well that are more sophisticated. On Linux, there's also the terminal. On Windows, there's either third-party applications, specifically this application which I have used, Obiectives. And probably you can also use just the new Windows 10 bash shell, but I've never done that. Does anybody have experience with that in here? It works? Okay, so yeah, that would probably be even simpler if you don't feel like downloading third-party software at this point. Then you'll need to have some way to transfer files. Again, if you're using terminal, there are a lot of terminal commands to do file transfer, like rsync or secure copy SCP. And then if you want to use GUIs, you're going to need to use something called X-forwarding. Which just allows you to display graphics for these programs over a remote connection. I think with Linux, the X-forwarding application is automatically installed on most distributions. On Mac OS or OS X or whatever it is that people are currently using now, I believe that you have to install X11 support manually. I learned this the hard way when giving the tutorial last year. There is an application in Mac OS that says you have X11, but then you click it and it says okay, now you have to download and install X11. So that has to happen, at least as of 10.9, I think. So these are just what a shell looks like. This is what it looks like in OS X on the left, and then Obiectives and Windows on the right. So I would say now is a good time to try connecting to OpenMind if you haven't already by using the command SSH. And then since we're going to try using an X-forwarding, use the argument -x. And then as the option -x, and then as the argument to the SSH command, which comes after all the options, you're going to type in your account, which is your MIT username at openmind7.mit.edu. That's a typo. I forgot to update that. At this point, if you have an account, or regardless of whether you have an account, you'll be prompted for your MIT password. If you enter it and you have an account, you'll be logged in. If you don't have an account, it will just say that. What does it tell you if you don't have an account? Just will fail. Okay, so how many people are logged into OpenMind right now? Okay, so now we're going to go through a few examples of actually running jobs on OpenMind. A caveat for this particular tutorial is that I think a lot of people are on OpenMind today, and I didn't want to go through the trouble of like trying to get a special partition so that we could our jobs would all run instantaneously. So some or all of you, these jobs may not run right away, and that's fine. That's sort of exactly how OpenMind is meant to function. So if everybody try to type this, just srun space hostname. And your job output, your output should look something like this. Initially, you might just get this output, which means that your job has been queued, and the Slurm is trying to decide when to run it. It's waiting for some other jobs to finish. And when it actually runs, you'll get the output. It'll tell you that the job has been allocated, and then the output there will tell you what node that task has been delegated to. But this isn't really how Slurm is intended to be used. I mean, we're not supposed to have to sit here and wait for our jobs to run. The point is to submit it and then you can walk away, or submit 100 jobs and you walk away, and as they complete, you collect your output later in an output file. So if your job is finished now, that's great. If not, you can just hit Control-C, or I think Option-C or Command-C on a Mac to cancel the job. Next one. So batch jobs is what the majority of jobs are going to be. These are jobs which are executed in the background once resources are available. So you submit a batch job to Slurm, and Slurm runs it when it can. Typically, each job will be defined by 2 or more scripts. The first script is a shell script, sbatch script, which asks for a resource allocation and then contains a command to launch the job. Now that command will contain the name of your job script, which defines the actual task. For instance, you might run a MATLAB M file or FreeSurfer or something in Python or whatever, and then the output of that will go into an output file or several output files, depending on how you've set up your script. And then you'll get, just like in this previous example, you'll get your job number when that's submitted. So sbatch requests resources. So what are resources, and how do we specify them? So like I said, the resources are the things that Slurm manages. They're CPU, memory, and sometimes GPUs. You specify them using options. So the form of this is dash with a single letter flag and then the value. Or you can use the long form flag followed by an equal sign followed by the value. So for example, we can use the sbatch command with the argument, or with the option -n1, which says that we want Slurm to run 1 task. Another way of writing this would be, say, --n tasks equals 1. Some options only have a long form flag. And all of these can be looked up in man pages, like online manuals. There's a few other resource options that are frequently used. -C, or CPUs per task, is the number of CPUs that you want per task. A lot of times you won't have to specify this, it'll just be 1. But if you are doing something that's, say, inherently, like a larger task that, for instance, is going to do its own sort of parallelism like MATLAB can do, you might want to specify 10 CPUs for task. Memory is the amount of memory per task, and this you have to sort of get right, because if your task tries to allocate more memory than you have allocated with this parameter, your job will fail and get canceled. And you can either specify that as total memory or memory per task. Again, and n is the number of tasks. There's an interaction between n and c, so the number of resources that you get often are n times whatever you use for c, and --mem per CPU. Big N is the number of nodes, like physical nodes. There's some cases where you'd want multiple nodes, but you typically, I think, don't have to use that one. And then time, that's an important one. So this is a limit on the amount of time that the task can run. you want to have the time be large enough that your job isn't going to fail because it times out, but you don't want it to be very large for scheduling purposes, and I'll talk a little bit more about that later. The default, I think, is still 1 day. Yeah, 1 day. So if you don't specify this, it'll give you a time of 1 day. Yeah, and I'll have kind of a section of best practices where I'll go through all of the things that you can do to help the scheduler run smoothly. Okay, so here's an example, a quick example of a batch script. So anybody, again, who's logged in can sort of follow along here. Just type vim, which is the name of an editor that I use, space testscript.sh. Vim is a little bit weird. If you have a different editor that you like to use, by all means use that. If you've never used an editor before through terminal, you can try this one, but you need to type I to put yourself in insert mode before you can actually enter text, and then control enter to exit insert mode. So this is the script. It's very short. The first line here is specifying to the sbatch command the shell script interpreter. This will just go at the beginning of every script. It doesn't have to be bash. You can use different interpreters, but this is a common one. And then you specify your resources. All of these resource requests are prefaced by your pound sbatch, which is a special message to the sbatch command that this is a resource specification. And then following all that, then you have your actual tasks. In this case, it's just host name twice. So what this is going to do is it's going to request 1 CPU and 100 megabytes of RAM. In the default queue, because I haven't specified a queue, talk a little about that later. When started, the job runs the first command, and then it runs the second command, and the output of these commands gets to an output file. So if you have this script finished, if you've entered all this in, if you're in Vim, just type :WQ to save and exit. And then enter sbatch test.sh. It'll tell you the job is submitted. And then once it's finished, depending on what the queue is looking like right now, I don't know, you can print the output file, which is going to be just slurm dash the job ID that you were told that you were given as the output of the sbatch command .out. You can specify a different name for an output file if you want. That's just the default. And then basically all this out file is going to do, it's going to show you what node that this job got allocated to twice, because we had the task, the host name twice. And you guys can stop me if you have any questions or if you're having difficulties with this. Okay, but that's a pretty simple job. It's only doing one task essentially in two tasks, but in sequence, in serial. And the whole point of OpenMind is we want to do high throughput computing. So to do high throughput computing, there's several options. One is you can queue up tasks that use applications which are inherently parallel, such as MATLAB. And like I mentioned previously, in this case, you're going to want to request extra resources for your job. You can use shell scripts to programmatically set multiple jobs in a loop. You can use single scripts to perform multiple parallel tasks. And you can also use job arrays. Each of these has their own advantages and disadvantages, and I'll just go through an example of a few of these. So the first is submitting parallel tasks with using the srun command in batch scripts. So if you remember, the first thing that we did was we submitted a job using the srun command. And when we did that, we had to wait for the queue, and then the job ran, and we got the output all in real time. When you use srun in sbatch, what it does is it doesn't really make sense based on the other use of srun. Srun kind of has two completely separate uses, it seems like. One is, like we already saw. The other is you use it inside of an sbatch or command to initiate parallel jobs. And the way that works is you request your allocation in sbatch and say you're going to have 5 tasks. And then when you do your srun followed by the command you want, it does that command 5 times in parallel. Basically, that's really all it does. It's not necessary for scripts when you're just running one task. So let's give a quick example of that. So I called this file test script parallel. It's very similar to the other script, except you're changing the number of nodes and tasks to 2. And then you're adding srun before the command hostname. And there's a typo there. The second srun is capitalized when it shouldn't be. So what this is going to do is it's going to request 1 CPU and 100 megabytes of RAM for two job steps again in the default queue. What's going to happen is it's going to call hostname twice in 2 separate tasks on 2 separate nodes. And so the output file is now going to look like this. You're going to get node 2, node 3, node 2, node 3, because that's where this job ran in this particular instance. Another way of doing this is using job arrays. In this case, we're going to use a script more like the first example, where the number of nodes requested and number of tasks is 1. And then we're going to add a new command just for the demonstration, which echoes an environmental variable called Slurm array task ID. And this environmental variable exists because what we're going to do is when we submit the job, we're going to add the command array equals 1 to 2. And what that is going to do is it sort of creates a job submission hierarchy. There's on the top level of the hierarchy, there's the number of the job array. And then within that job array, there's going to be individual jobs. And you can learn more about that, again, through the manual pages, the documentation online. But suffice it to say here that this is just a way of sort of parameterizing many tasks. Because what you can do is you can actually pass this environmental variable to your application to let it know like which instance number it is. The instance number is going to change what kind of computation you want to run. So another thing you can do on OpenMind is run interactive jobs. So far everything we've done is you submit a job, the job runs either in the background or in real time, and then when it's done, it's over. If you want to do something like run a bunch of small commands interactively or debug some code, you can run an interactive job, and this is the way you do that. You should run it on. You don't need to run it on the interactive partition, but it's helpful. And the way you do that is using the -p option followed by the name of the interactive queue, which is Interactive, and that's just basically one of the nodes is set up to have, I think, a especially large amount of RAM and cores to just exist for people to run interactive jobs on. And you have to remember the PTY argument, or else you won't get to log in on the node to run your commands. And if you want to use the GUI, you're going to want to call this with X11 forwarding. You use the --X11 option. I just put in the GPU request there to show you how to request GPUs if you want. And then, for instance, to run MATLAB on the interactively through OpenMind. This is the commands that you would use to do that. And I can show anyone afterwards if somebody wants to actually see that. So there's other useful options. Array, we talked about that. There's also, you can set up dependencies. So if you have multiple jobs and you need the second job to start after the first one finishes, but you don't want to wait around to submit the second job, you can specify the job number of the first job as a dependency to the second job. You can have Slurm send you emails when jobs start or finish or fail. You can specify particular partitions, like for instance, the interactive partition. You can select different qualities of service. This is sort of like a partition, but it's not tied to any physical set of nodes. So for instance, on OpenMind, there are 3 different QoSs. There's the normal QoS, the use everything QoS, and then the individual groups have their own higher priority QoSs if they need something done very quickly. And the way those are organized is on the use everything QoS, that's the lowest priority. You can submit as many jobs as you want. You can be using as many resources as you want at any given point in time. But if somebody runs a job on the higher priority QoSs, then your jobs will get preempted. So say a lot of jobs that are all low priority, you might want to use this. Then there's the normal QoS, which is what your job will get submitted to if you don't specify. You have, I think you can use up to 1/3 or 1/4 of all the resources at one time. Most people won't get there, but some people definitely will. And this is sort of the default QoS to keep us from running into the situation where one person manages to use up all the resources at any one point in time. The way that OpenMind is managed, the goal is to allow everyone to submit as many jobs as they want. We don't want we don't want individual users worrying about overloading the cluster, but we don't want users to overload the cluster. So we're trying to the Satra and the admins have sort of come to this as a happy medium. And then the individual lab QoSs, you're limited in the number of resources you can use by quite a bit. I think the standard is for the base subscription is 2 nodes or so, about 2 nodes. So it's about 40 cores, 500 gigs of RAM, and I think, 4 GPUs? 5 GPUs. And so using that QoS, you'll basically get your job submitted instantaneously. But again, like I said, you're limited in how much you can execute at any one time. And then exclude, actually that's not very useful anymore. That was useful when the standard partition overlapped with the interactive partition, and sometimes you'd get put on the interactive partition and then booted when somebody ran an interactive job. Forget about that. Okay, so simple best practices. One, don't run anything on the login node. Now this doesn't, I don't mean like, don't like browse your directories and edit code. I mean like don't run jobs. Don't like run MATLAB on the head node. Don't train RNNs or don't train deep networks on the head node. Be as accurate as possible when you're specifying resources, in that you should specify as many as you need and no more. Because like we said, for instance, if you don't request enough memory, your job will fail. If you request too much memory, then you're going to be using up resources that other people could use, and it might make your job harder to schedule. Because remember, the scheduler has to make sure there's enough resources open to fulfill the request that you've made. The other thing is there's something called the back scheduler. And what the back scheduler does is every few minutes, it looks through the queue of jobs. And if, let's say, the job with the highest priority is very big, and there's some free resources, but not enough to queue this job, it'll go down the list and try to find a job that A, is small enough to run right now, and B, will definitely be done so that jobs ahead of it, done soon enough so that jobs ahead of it won't be delayed. So if you specify time as something very small, you're more likely to get backfilled and have your job run faster. Also make jobs, if you can, granular to aid in scheduling. It's a lot easier to schedule a job that requires one CPU on one node than it is to schedule a job that requires 20 CPUs, because that means you have to wait for a whole node to be free while all these other jobs are completing asynchronously. That doesn't mean you have to only request like one task per job. You can request 100 tasks, but each task should be as small as possible. And then the last thing is even though we want to have everybody be able to submit as many jobs as they need, be reasonable. I think once we get into like thousands of jobs, especially like if single users are submitting thousands of jobs at one time, choke just the queuing system. So if you have to do a lot of jobs, use either parallel jobs or job arrays, or just use like as a last resort, you can write a script that sort of limits the number of jobs you can be running at one time. I think some people have done that, but most people I think would have to worry about it. And then in terms of, I don't think we really need to talk about cluster upgrades. The cluster is pretty upgraded at this point, right? I don't know if we have any. Are we still planning on expanding?
Not immediately, but if somebody wants to contribute,
right.
welcome back.
If your PI or your group wants sort of especially more dedicated resources, anybody who contributes, like for instance a node, that is added to your personal your group's QoS. So not only does it expand the cluster, but it directly expands the amount of resources that you are allowed to use exclusively if need be. Otherwise, anybody can use it. And that's all I have. If anybody has any questions, I can answer them, or, yeah. Yeah. I don't remember off the top of my head the command for that. Is it? Yeah, and there's a ton of options on that command. Like you can see almost anything you would possibly want to know about the job. Yeah, so if you want to know how much, like if it can be hard to predict ahead of time how much resources a particular job is going to use. So something that people will do is they'll run the job asking for more resources than necessary, and then they'll go back and use a command called saccount or SACCT to look specifically at what resources the job actually used. And then for future job submissions, you can sort of pare down your request to meet those minimum limits. Okay, so I guess I will have Satra come up now.